not at all straightforward, right?
No,
Not at all.
switching, we'll go, first we'll do this, then we gotta stop that, and then we'll go back and do this, and we're gonna keep using recursion methods and everything else.
So wonderful math and wonderful ideas, right? Okay, Jeremy says no.
I don't know who comes up with this stuff.
Mathematician and Hermite. I mean, Hermite, for the conclusion at the end of the analytic solutions, you come up with polynomials that are called Hermite polynomials. And so you do all that work for the first time, and you get these polynomials named after you. Right? And that's what Hermite did. Okay, what is the second way that we emphasized here? Using the operator method. All right, and we use the raising and lowering operators. And once we went through all the gymnastics of the operators having to do with the commutation relations and everything, we came up with a definition of the raising and lowering operators, right?
Yeah.
We also found out a way to re-represent, that's kind of redundant, to give a new representation of the Hamiltonian in terms of raising and lowering operators, right? And when we did that, we found out that the raising and lowering operators gave us nice properties. For example, when we use the raising operator on a wave function, what do we get?
The next energy level.
We get the next energy level up. We get the wave function, the next higher in energy wave function, and we get the actual next energy eigenvalue. What is that energy of the eigenvalue with respect to the one we raised from? How is it different? It's different. It's raised by h bar omega, which is
The energy of the photon or quantized
it's one quantum of energy. That's right. Okay. But we also found that we could do a trick. All right. And with this trick, what we saw is that we have wave functions, and what we did is we thought about the infinite well. And in the infinite well, we saw we had the lowest wave function that was non-zero. And then below that, the wave function was truly zero. So we call the lowest wave function, the lowest state that's non-zero, the ground state. And how does the trick go for using raising and lowering operators so that you can solve for all the wave functions, starting with that ground state?
Go lower or zero.
Okay, so go A, lowering operator on psi 0, and what does that give you?
0.
0. The lowering operator is a differential operator. So you have a differential operator acting on psi 0 equals 0, so then what can you do?
Just add the other operators.
You can solve for what? So lowering operator on psi 0 equals 0. Now we can solve for
Psi 0.
psi 0. So we've solved for the ground state. Then once we have the ground state, what can we do?
What psi 1 was ground state? The text did have psi 1.
So I told you to be careful. For the infinite 1D well, we numbered the ground state n equals 1. All right, because that's the lowest energy level. I talked about this in class.
Yep.
But in general, you could call that n equals 1. This is what Griffish uses, the ground state. You could call it the ground state, call it psi 0. But the quantum number is n equals 1.
So psi 0.
The psi 0 is really the ground state.
Psi 0 is the ground state,
All right.
which for the harmonic oscillator is truly n equals 0.
Okay.
Right? That's the vacuum energy density. Okay, that gives you the half a photon of energy for n equals 0. Okay, but that's not true for the infinite well. The n equals 0 is the wave function is 0. Okay, everybody see that? So again, the ground state is not going to depend on your quantum number, n equals 0, n equals 1. What we'll call now the ground state is the lowest non-zero wave function. Okay, so what we came up with is we came up with this. And this is all I really say, is that we found psi 0 of x equals m omega over pi h bar to the 3/4 e to the minus m omega over 2 h bar times x squared. We found E0 equal to h bar omega over 2. Then what we can do with this is from this ground state we can create psi n of x equals 1 over n, square root of n factorial, a plus dagger to the n of psi 0 of x. All right, with en equal n plus a half h bar omega. Okay, so I suggest to you, and this is why I wanted everybody to look at the analytic form, which way was easier?
This way was much easier.
Okay, this way was easier. But I've got to tell you guys, if you do not struggle through the analytic solution, you will not appreciate that fact at all. So I don't know what I can do to make you do it, all right? But go over the analytic solution, all right? Okay, cool. Last thing. So now, so these solutions are what? What are we going to call these solutions? What's that?
Stationary.
They're stationary. Why are they stationary? Okay, they don't have the time dependence. We took out the time dependence by separation of variables. Okay? So we also know that they're solutions to Schrödinger's equation, right? So they're stationary. They come from separation of variables. So what can you tell me about all these functions, this infinite set of functions?
They're square normalizable.
Okay, well, first of all, okay, they're square normalizable. And because they come from a separation of variables, they form an infinite basis set. These are the normalized stationary solutions, yes.
Is it like a 4 properties they're talking about, like one normal, one complete?
So if they're square integrable, they form a complete basis set. Then they have all the properties of a vector space, which include the dot product, and the dot product, I guess, and they form an infinite basis set, and they're Hilbert. And therefore, if that's the case, what do we end up with? We end up with a great basis set to expand the solution onto. So we can create the most general solutions in what way?
Like linear combinations of.
As a linear combination. So, how am I going to write down? So here we go. H O, unperturbed harmonic oscillator, times psi of x and t equals IH partial of psi with respect to t. That's the time-dependent Schrödinger's equation for the harmonic oscillator. The most general solution looks like what? Psi of x and t is going to equal, go ahead. What is it? Let's start with a summation, right?
Summation of n equals 1 to 0 to c to the n.
We use summation from n equals 0 to infinity of Cn.
And then square root of 2 over a sine.
Okay, I'm with you, Matt, but let's throw in the time dependence right here.
Oh, okay.
The time.
Okay, you want to do it at the end?
Yep.
One first.
So e to the minus IEn over h bar t. Right?
Can we just put what E
And then you plug in the en. So en's are going to equal these things. Right? So let's let's do that. I like that element. Let's make it completely as it is. It's going to be n plus a half h bar omega times time. Right? And then it's going to be all this stuff. 1 over n factorial, 1 over the square root of n factorial, a raised, a plus n on psi 0, and psi 0 is m omega over pi times h bar, so pi h bar to the 3/4.
I thought it was still 1/4.
I may be wrong. E to the minus m omega x squared over 2h bar. Is it a fourth or 3/4? 1/4 or 3/4? 1/4, thank you. Alright, so it's a bit of a monster.
Probably just normalize that, right?
This is normalized, right?
Right.
And these are the projections onto the basis set. Isn't this fun when you can look at it and say, oh, I know what this is now? I mean, it's nice.
Well, it's less horrifying, certainly.
Not really that fun.
Yeah, but it's nice to know that. Okay, so then for a real problem, what do you want to solve for? Like a real problem goes like this. I would give you psi of x of t equals 0 equals something. This is given. What do you want to solve for then? Say that again, please.
T equals to 0, so we can solve for this dash x state. And then we can solve for Cx.
Okay, so we're looking for the CNs, all right? Of a measurement finding the harmonic oscillator in that given state n. How do you solve for the CNs? Fourier's trick. All right, so let's write it out. So I expect you guys all to be able to write it out. So CN is going to equal what?
Integral.
The integral.
That times psi of n.
Okay, it's going to equal this thing, psi of x,
And t equals
comma,
zero.
t equals 0,
Times psi of n.
times this, times this thing, but at t equals 0. So at t equals 0, this thing drops out, right? So then it's going to be, let's see,
Psi of x.
Yeah, it's psi n of x, right?
So psi star.
yeah, we can just leave it as psi, let's just leave it
Yeah,
as
that's
psi
pretty normal.
n of x dx, that's fine, instead of writing everything out. Where all this stuff is,
Where that's, yeah.
yeah, that's psi n of x. Okay.
So this is just basically psi of x squared. Because if t is 0, then
Well, I would give you this as some function. All right, this is kind of what we did. This is homework problem 2.13. So 2.13 is this exact problem. Okay, now, is this anything different than we did for the infinite 1D well?
No.
No.
Well, just the,
The only thing that's
Psi n of
different
x.
is the psi n of x,
Yeah.
the stationary state we found in the time-independent solution.
but it's always the same for every harmonic oscillator.
For the harmonic oscillator, it's always the same. What's different are the k's and the m's and things like that. All right. And so, is the story the same thing? Okay, that's the thing that's important. If we're going to do the same story, you know, Mike's worried about hydrogen. This is the same story that we're going to do with hydrogen. Exactly the same thing. What do you think is going to be different for hydrogen?
Psi n of x.
The psi n of x. It's going to be three-dimensional. It's going to be x, y, and z. But everything else is the same. All right. A question that you can ask, it's a slightly simpler question that you can ask, is instead of concentrating on this general, the total wave function that's general, example problem number 2.5 asks for the expectation value of the potential for the nth stationary state.